Being very careful not to short anything. Now that's interesting, 3.08 volts. That is definitely not right. Welcome back to Cloud 42, I'm James. We are taking a quick break from the electronic lead screw project, mostly just because I haven't had any time to work on it the last couple of weeks. In addition to the shop organization project that I've had going in the background for a while here, my day job has also become pretty intense lately, and I've also had several repair projects that have come in recently that have taken up my time. Now, I'm pretty sure you don't want to watch me sorting through 25 years worth of leftover screws from other projects, and I'm pretty sure you don't want to watch me wrestling with cloud infrastructure, scalability, and performance issues. So this time we're going to take a look at one of the repair projects that came in this week. This is a PC board out of a DMX lighting distribution amplifier. Now, if you're not familiar with it, DMX is a protocol that's used to control stage and theater lighting. So you're going to see it any place from, large concert venues to theaters to concert halls, houses of worship. You're going to see it in clubs. You'll see it even used for, portable DJ lighting units. And the way it works is you have a central controller like a lighting desk or board with a bunch of faders on it. And then it produces a signal that goes out to control the fader packs for controlling like traditional tungsten lighting, or it'll go directly to the lighting instruments in the case of modern LED lighting. And so you've got this signal that's sent out by the board or sent out by a computer more commonly today. And that has to be distributed and sent to each and every lighting instrument in the setup. And there can be hundreds of these. And the DMX protocol is designed so that you can just fan out and connect a bunch of instruments to one output, but there's a limit. And since common theater installations or common installations in concert halls or churches are going to have potentially 100 or more instruments involved, you're not going to be able to just chain those all together on the output of a USB DMX card. So the solution is a distribution amplifier. And I'll throw up some photos of the one that this came out of. And the way this works is it's a card cage that's got a bunch of cards in it, just like this one. And each card takes in a Virgin DMX signal from the input, processes it, and creates several separated, isolated DMX outputs to go to more distribution amplifiers or to go to the instruments themselves. Now, this particular board has some kind of electrical fault. We're going to need to troubleshoot it and figure out exactly what's going on. When this was in the distribution amplifier, the lights that were connected to this particular board were flashing and flickering and putting on a light show even when the operator didn't want a light show. And I actually saw it happening. And you can kind of tell from the way the lights are flashing what's going on. If it were a power problem, power fluctuation, you would expect to see all of the lights on a particular dimmer pack or all of the lights on a particular circuit kind of flashing in unison. And that's not at all what was happening in this scenario. In this scenario, the lights were all flashing independently. Every circuit was flickering. There were some RGB fixtures that produce colored light, and the different colors were all flashing at different times and different colors. And what it really looked like, when I saw it, I immediately suspected it's some kind of a data problem. The way DMX works is it's sending out a burst of 512 numbers, and those numbers are the values for the brightness for each individual lighting channel. So every fixture knows which number it is. So if it's number 138, it'll see that burst of numbers come down the wire, wait until it gets to the 138th one, pull that value out and set its brightness. And then a few milliseconds later, another burst comes and it's just continually doing this, finding its number. But instead of finding its number consistently, it was coming up with garbage data and flickering all kinds of different brightnesses and all kinds of different colors. And since every instrument was doing this differently, it really looked like it wasn't a systematic problem. It was a noise issue, or it was a problem with the quality of the DMX signal or something. And so we immediately looked at the distribution amplifier. Now, conveniently, the amplifier had 3 of these boards in it. So it was really easy to note that the instruments that were misbehaving were all on the same board. So we pulled the board out, swapped it with another one, and that solved the problem. Everywhere we put this board, the problem followed it. So the problem is definitely with this PC board. So we pulled it out, and I've got it here on the bench, and our job today is to figure out what is wrong with it and fix it if we can. I did some looking online to see if I could find a service manual for this device, and I came up empty. I did find some people in forums asking about them and saying that nobody was able to find one. I couldn't even find a user manual for this, and the discussion in the forums is that there never was a user manual for this thing. So that's going to leave us to just look at the board and try to decipher what's going on just from the overall layout and the component choices, and then dig in and try to see if we can, once we figure out how we think it's supposed to be working, dig in and try to figure out what's wrong with it. Now, the first thing I notice on this thing is that it is definitely designed for service. There are fuses everywhere. There's a row of fuses on all of the DMX lines down here. There's a fuse right here on the input. And this is really amusing. There's 2 fuses up here that are just marked spare that are not connected to anything. So they actually put spare fuses right on the board. In case you blow one of these, you'll have a spare handy. The other thing I know is that all of the chips are socketed. So this thing was designed to be serviced, clearly. And interestingly enough, there's a chip up here in the corner that has no connections to it at all. Looking at the front of the board and looking at the back of the board, this is just a 2-layer board. There are actually no connections to this chip at all. So they've actually included a spare chip on the board too. So this is really encouraging that this was actually designed to be serviced. Now, the next thing I noticed is down the side here, we've got 3 big transformers. And these look like AC power transformers to me, each with 2 outputs on the back side. So every one of these transformers, they're all connected up in parallel on the primaries, and then the secondaries each have 2 secondaries, so 2 outputs. So that would be 6 separate secondary outputs on the transformers, and then down here looks like 6 independent power supplies. There's 6 voltage regulators. These are all 7805, just standard 3-pin 5-volt TO220 voltage regulators. There are 6 electrolytic filter capacitors, and if you look down in between there are 6 diodes. So clearly what's going on is we've got 6 independent power supplies. So you have an output from the transformer, it's run through a diode as a half-wave rectifier, then you have a filter capacitor to smooth that out into an unregulated DC voltage, and then you have a 5-volt regulator to produce a 5-volt regulated supply. So this device is, let's see, do we have any dates on here? Across the top here, there's a copyright, 1993. So this is a 1993 vintage design, which explains the through-hole components and the 5-volt 3-terminal regulators. See if we can find a date code on one of these chips. Let's see when this one was actually built. See, I see 0048, so the 48th week of 2000. And in fact, on these chips, I see another 0048. So this was built sometime, at least the chips that are on this were made sometime around the end of 2000. And that makes sense. That's about the vintage of the building where this amplifier was installed. So that means that this amplifier has been plugged in, powered, and running for probably about 20 years. So why would we want 6 independent power supplies? Well, the answer is that DMX operates in a noisy environment. You've got huge dimmer packs potentially doing pulse width modulation on multi-kilowatt lighting circuits. That's going to generate a lot of noise. Plus you're dealing with long cable runs in a building or even in an outdoor venue where the sending equipment and the amplifying equipment and the lighting instruments themselves are all on different circuits. Sometimes they'll be running on generators, so they won't even share a common building ground, and you can have ground voltage differences. And so DMX is a differential signal. It sends two signals on two wires, and these are just the pulses for the signal, the digital signal, and the inverse of that. So the receiver doesn't have to have a common ground. It can just look at the difference between those two voltages to decode the data. And in fact, if you can have all of your amplifiers and all of these channels electrically isolated from one another, you're better off, because then you don't get any current flowing through ground loops and you don't have to deal with any of that. You can just plug this stuff together and not worry about it. And that is exactly what's going on here. Now, these are obviously organized into multiple strips. This particular board produces a pass-through signal, so DMX comes in, it produces a signal that goes back out to the next board in the rack, and it also then produces 5 independent outputs. And so that's what we've got going on here. We've got the amplifier chain for the pass-through, and then we have 1, 2, 3, 4, 5 isolated amplifier chains for the output. And so what's going on here is this chip is a differential transceiver, so it's receiving the signal. It's wired up on the back here. I won't flip it over. And then there's a hex inverter, and then another transceiver that's transmitting the output signal. And so this is all on one independent power supply. Signal comes in, signal goes back out. This inverter is then used to buffer the signals and drive 1, 2, 3, 4, 5 optocouplers. These are 10 megahertz high frequency optocouplers. So this inverter is just being used to drive the LED inputs so then this is on a separate power supply, each one of these, and it's optically isolated here, so it shares no common ground with any other part of the circuit. And then that signal goes through another hex inverter to another transceiver that's then transmitting out through these fuses an independent DMX signal. So we've got 6 power supplies powering 6 independent amplifier channels. So the very first thing we want to do is just sort of do a visual inspection of the board. And I've kind of looked this over. There's a bunch of obvious things we can test. We've got a whole bunch of fuses on here, and given that the fuses are right there, it seems like those would be a good thing to check. And all the fuses are good, including the spare. I can also see the rectifier diodes down here, and those would be something reasonable to check just because we can and because they're easy. So that's a diode. Let me make sure I put these on the right way. 4.91 volt drop, that seems pretty reasonable. Having trouble probing these. 0.5 volt drop, that seems about right. Half a volt, 0.5 volt, 0.498. Yep, so all the rectifier diodes look good. I would immediately start to suspect the capacitors just because of the age of this thing. These look like decent capacitors. These look like United Chemicon 105C rated units. That's a top flight Japanese capacitor. I don't see any bulging. There's nothing going on there that makes me suspicious, just except that because of the vintage of this thing around 2000, and because they're electrolytic capacitors that have been in service for this long, you immediately start to wonder. Look at the back of the board. Now this is interesting. Can you see this? It looks just a little bit toasty right here, and this is around one of the voltage regulators, so that's also suspect. They all look like they've been warm, but that one looks like it's been a little bit warmer than the others. We want to keep that in mind, so that's the second voltage regulator up. That's certainly suspect. But at this point I don't see anything obvious. There's no bulging caps. So I think the next thing to do is probably power this up and look at it in operation and see if we can tell what's going on. Now, I don't have the card cage here, so I'm going to have to just try to power this up. And I've been kind of looking at this, trying to understand exactly what we've got going on. And I think what I'm going to do is just solder a connector onto the back of this. The resistance between these 2 points, let's turn that off. Okay, so these 2 points, this second pad here and this end of the fuse, that's the transformer primary. See, 67.5 ohms. That seems about right for the voltages we're dealing with. So let me tack a power connector onto here, and let's use that to power up the board. And just as sanity check, let's check the resistance across the input here. 68 ohms, that looks about right. Okay, now I'm going to power up this board, and it's important to understand there's 110 volts on the primaries of these transformers. Now that power is going to appear on this card edge, and it's going to appear on all of these connections down here for the transformers. Everything from this side of the board over should be low voltage, so we should be relatively safe handling it. But it is important to understand that this is not something that you want to take on if you're not certain what you're doing. Especially because, again, this side of the board's live, 110 volts, and you do not want to come across that. It will bite. So don't try this at home unless you know what you're doing. I don't really have a choice here, so I'm going to go ahead and power this up, and let's see what we can see. Okay, so this is all live. I'll handle the board from this other side. Now the first thing I notice is that most of the LEDs on the front edge of this thing are powered on. Now what's going on here, there's a power, the top light, or the light, one of these lights is a power light and the other light is a data light on each channel. So this is the input channel, and we've got power, the data light is out, but all of the other ones, the data light is on. So the data light being out here makes sense because there is no data being input to this board. However, all of the output channels think they're getting data. That's definitely a clue. And so I would immediately suspect, just based on that, that there's something wrong with the input channel here, because it thinks it's getting data and it's, I'm presuming, transmitting that data to these other channels, and they are interpreting that as data, or at least interpreting that as some kind of signal. So the first thing we want to do is test the voltages on the board. And I've got, again, 6 independent channels, and these are handily 74 series logic chips. So I know the pin outs of those. I know this pin is ground, and I know this pin should be plus 5 volts in this case. So let's actually take some voltage measurements and see what we actually have. Being very careful not to short anything. Now that's interesting, 3.08 volts. That is definitely not right. Check the other channels. 5 volts, as expected. 5 volts. 5 volts. 5 volts. 5 volts, 4.996, close enough. But this first channel is not 5 volts. 3.143. That definitely does not look right. And that one is actually, if we follow the traces here on the board, connected to this voltage regulator, the one that looked a little bit toasty on the bottom. So the first thing I would think on seeing that is maybe that voltage regulator has failed. Now, you have to be a little bit careful about this. These are 7805s, and the 78 series regulators are really, really robust. They are, they have all kinds of protections in them. They have thermal shutdown. These are run without heat sinks, but there's not a lot of load on them, so it's probably not a big issue. And if they get too hot, they just shut down anyway. So this thing could be in thermal shutdown, except, yeah, it's warm, but it's not, you know, hot. These things can go to a junction temperature of like 125 C. before they shut down. So I don't think that's it, but I would immediately suspect maybe this regulator has failed because it's outputting only 3.3 volts. Another possibility is that there's something in this circuit that's shorted and it's dragging that voltage down. And if that were happening, able to pull a 1 amp regulator down, first of all, this thing would be blazing hot, and it's not. And also, one of these chips would be hot. And they're not. They're just, slightly warm, as you would expect, same as everything else here on the board. So it's probably not that. Now, one other thing that I would suspect, like I said from the beginning, is it's this capacitor. Now, how does this work? Let me unplug this for a minute. Let's talk about what's going on in this circuit. So we've got a transformer that's outputting an AC voltage of some kind. This is going through a single rectifier diode, and then there's an electrolytic capacitor here. Then that's going into a voltage regulator, and this is outputting plus 5 volts, or in this case only plus 3, and ground. So this, because we've only got a single diode, it's a half-wave rectified voltage. So instead of the AC voltage that would be like this, we're getting a half-wave rectified AC voltage that looks like this. Then it goes through the capacitor, and the job of the capacitor is to smooth this out. So the voltage rises, it charges the capacitor, then the capacitor maintains that voltage until the next pulse tops it off, goes down slightly, but it maintains that voltage. So then you get this DC voltage that's got some ripple on the top, but then you go through the regulator and this cuts it off, and what you get is a nice clean 5-volt signal. But we're only getting a 3-volt signal. Now, one of the things that could be happening here, if this capacitor has failed, is it will not be smoothing this out. And instead of smoothing out this ripple and giving us a nice consistent voltage that's above the 5 volts we're trying to regulate, you can end up with a really messy voltage that looks something like this. And if this is dropping below the voltage you're trying to regulate, then you won't get DC on the output. You'll actually get something with some AC ripple component. So the best way to find out if the capacitor has failed is with an ESR meter. I don't have an ESR meter, they cost money. But since we have the circuit actually up and operating, we can measure the ripple voltage. Let me plug this back in. Now this is something that some people don't realize is I've got my meter set to DC volts here. So when I measure this, I get 3.146. The thing to remember though is that's not necessarily a DC voltage. If you try to measure an AC voltage or something with a bunch of ripple, you'll get an average voltage here. But what you can do is switch the meter into AC mode, then go back and measure your DC voltage, and it will measure the magnitude of the ripple. And you see that? I've got 1.38 volts. Now that is an RMS number, so the peak-to-peak number is actually quite a bit greater than that. I'm moving the probes here, but I've got almost 1.4 volts of ripple, and that's after the regulator. So prior to the regulator, we've definitely got a whole bunch of ripple, which means this filter capacitor is not doing its job. Now, just out of curiosity, let's check the other ones. 0 volts, 0 volts, 0 volts, 0, and 0. Yep. So we have found our culprit. That filter capacitor is bad. In fact, there we go, 1.628 volts. So we've definitely got a bad filter capacitor here that we need to replace. And chances are very good that's all that's wrong. And that would make sense. If that filter capacitor is bad and we've got nearly 2 volts of ripple on our 5-volt regulated supply, well, this regulator is going to run a little hot because it's trying to cope with that, switching on and off and going through its dropout voltage over and over and over again. And then that is going to generate a kind of a pulse train, a 60 hertz pulse signal in here, which is then being broadcast to these other channels, which is probably why their data lights are on. So I'm willing to bet that if we just replace that capacitor, we'll be good. Now, unfortunately, I do not have a place locally where I can go and buy capacitors like this. I could probably find one in my junk bin, and that would be okay for testing, but really with something of this vintage, I'm going to want to replace all the capacitors because this is going to go back into production, and I don't want to mess with this again in 6 months when another cap goes. So I'm just going to mail order enough capacitors to replace all of these. And so what I'll do is I'll go to Mouser or DigiKey or wherever, and try to find a capacitor that's a Japanese-made, high-quality cap from a good name brand with the same or greater capacitance and the same or greater voltage rating. And I'll order enough of those. There's 3 of these boards, and there's 6 in each, so I'll order at least 18 caps, and I'm just going to recap the whole amplifier, especially since that appears to be what the failure is here. Now here's a handy little tip for those of you who had the patience to watch this far into the video. I guarantee this one tip is going to be worth what you paid for this video. Now when you mail order stuff, the hardest part is always the waiting. But it turns out there's a hack to get around this. When you place an order at a place like Mouser, you get to the last page of the shopping cart, they will show you the date that they expect your products will ship. So if you're before the shipping order cutoff time for today, the order will ship today. And if not, it'll ship tomorrow or the next business day. It'll tell you this right on the web page. Now today is Saturday, and so they wouldn't ship today. So if I placed an order today, normally it would not ship until Monday. But in your web browser, when it's showing you that date, you can hit F12 to open the debugger, and then you can actually edit the date on the page before you submit the order. So when I'm done here, I'll go in and place my order, and it'll show me the date of next Monday. But instead, I'll edit the page, change the date to last Wednesday, select 2-day shipping, and then the order will be delivered yesterday. So as long as I remember to do that, then the package should be out on my front step now. Let me go get it. Okay, so there are the capacitors, and it looks like I'm going to be able to order the same Nippon Chemicon or United Chemicon caps. Those are good quality caps. And it looks like I'm also going to order replacement parts for everything else. So this is a couple of the differential transceivers. This looks like a couple of high-speed optocouplers. Got a couple of extra voltage regulators, a couple extra Schmidt trigger inverters, and another bag of capacitors. Why is that? Okay, this is a little bit embarrassing. It looks like I only ordered 16 because everybody knows that 3 boards times 6 caps is 16, and apparently I'm going to then realize my mistake and order 4 more. Well, at least they combined the orders. Okay, let's suck out this capacitor and see if it fixes the problem. Now, if you do a lot of through-hole board repair, this tool is worth its weight in gold. This is a Hakko FR301 desoldering pump. It just heats up the tip. It's hot, and then it has a vacuum pump in it, and it pumps air, and it'll suck the solder right up into this chamber. And if you're doing a lot of through-hole kinds of repairs, this thing is just amazing. They're also great for salvaging parts from old boards before you throw things away. So I've got 2 connections here on this capacitor. Let me just suck it out. Now heat it up, make sure everything is good and molten. Pull the trigger, and that joint's clean. And the other one. And that should be it. The capacitor comes right out. Let's grab another one and put it in. I gotta make sure I get the negative on the correct side. You don't want to install a capacitor, an electrolytic capacitor, backwards. It will pop almost immediately if you do. Clip off the extra lead length. That looks good to me. Let's power it up and see if we fixed it. One more check to make sure the negative's on the right side. It is. And being careful not to grab the hot side of the board. Hey, take a look at that. The power lights are still on every channel, but the data lights are now off. So I think that is a fair bet we fixed it. Check the DC voltage here. There we go, 4.965. I will take that, and let's look at the AC. 0 volts, exactly what we wanted. Well, that board is fixed. I am going to go ahead and suck out all the rest of these capacitors and replace them, and go put this board back into service. And while I'm at it, I will go ahead and grab the other 2 boards and suck out and replace all the capacitors in them as well. That's all I have for you today. Hopefully we can get back on the electronic lead screw project soon. I know that's what you're all waiting for. Of course, as I stand here talking to you, my car is sitting right outside that door with a blown alternator, so there's that. It really never ends. If you enjoyed this video, please give me a thumbs up. Feel free to subscribe to the channel and leave me a comment. I'd like to know what you think. Thank you for watching.